Welcome to the Deep Dive, where we cut through the noise and get you straight to the heart of what you truly need to know. Today, we're pulling back the curtain on those three little letters that seem to be absolutely everywhere in the tech world, API. You can barely open a tech article, listen to a presentation, or even just browse a new app without hearing about application programming interfaces. It feels like a secret language almost.
It kind of does, yeah. But for good reason they're the silent architects of our digital landscape. They really are. APIs are fundamentally reshaping how software is designed, how it's built, and crucially, how different systems talk to each other. Think of them as the invisible threads, the digital connective tissue linking so much of the modern world we interact with every single day.
And often without us even realizing just how intricate it all is behind the scenes.
Exactly, that intricate dance happening in the background.
Our mission today, then, is to be your personal shortcut to truly understanding APIs. We're going to demystify exactly what they are, why they've become not just important, but absolutely indispensable in modern tech, and, how they empower developers to build things that would have seemed like science fiction just a few years back.
Right.
Consider this your practical, no-nonsense guide. We've got some surprising facts, clear explanations, all designed to make you feel genuinely well-informed without feeling, buried by jargon.
Yeah, we've really stacked our sources for this deep dive. We've pulled from comprehensive tutorials on APIs, detailed guides on leading front-end frameworks like Vue.js, and some really insightful slides on core application development principles. It's a rich landscape and, honestly, pretty fascinating. We're excited to navigate it with you.
Okay, so let's start right at the beginning. Let's really unpack the I in API interface. What does that word even mean in this context?
Well, let's start with something super familiar. An old school radio. Think about the physical controls on it.
Okay, volume knob, tuner.
Exactly. The volume knob, the station tuner, the on-off button. These are all interfaces. As a user, you instantly know what they do.
Yeah, turn the volume up, it gets louder. Simple.
Turn the volume knob clockwise, sound gets louder.
Yeah.
Press power, it turns off. There's this intuitive connection between your action and the outcome.
And the beauty of it is you don't need to be an electrical engineer to use it.
Not at all.
You don't need to understand the transistors, the frequencies, all that complex internal stuff.
Right, the circuitry.
It's all hidden. That magic is completely abstracted away. You just get the controls you need.
Precisely. And interfaces, just like technology itself, they're constantly evolving.
Yeah.
Imagine that simple radio morphing into, say, an alarm clock radio.
Okay.
It still has the volume and station controls,
Yeah.
but now it adds new features. Setting the time, setting an alarm. Again, you don't need to know how the clock mechanism works or how it stores the alarm time in memory.
You just get the buttons to set it.
Yep. The interface provides intuitive controls for these new features. It keeps abstracting things away, but at the same time, it expands what you can actually control.
So we go from physical things, like a radio dial, to something we use constantly today. Graphical user interfaces, GUIs, like a streaming music app on your phone.
Perfect example.
You see that play button, tap it, music starts. You probably have no idea how it does that. The servers, the codecs.
Right.
But you're totally comfortable with that level of abstraction. Who has time to wonder about that when you just want to hear your playlist?
And that's the core idea. Now, flip it around. For the developer who built that music app, they do understand, to some extent, how the play button works. They coded it.
Right, they wrote the logic.
They wrote the logic so that when it's clicked, a specific action happens. But even they are working with interfaces that hide a ton of detail. For instance, the developer probably used something like an on-click event handler. That's a common interface provided by application frameworks like Vue.js or React. They didn't have to write the really low-level code that makes the button, visually react to a press or make a clicking sound. The button itself, provided by the framework, is an interface. It handles that complexity for the developer.
It's like building with high-tech Legos, isn't it? You don't have to worry about how the plastic is molded or how the studs fit.
That's a perfect analogy.
Yeah, you just use the ready-made bricks to build something bigger.
Exactly. And this abstraction goes even deeper. The code for that music app, it probably uses a media player API provided by the phone's operating system, Android or iOS.
Oh, okay.
This media player API hides the incredibly complex details of sending audio data to the actual hardware, managing memory buffers, audio drivers, all that intricate stuff. The developer just calls a function something simple like mediaplayer.play. And the operating system takes care of talking to the sound card or speakers.
Wow.
That's the real power of interfaces for developers. They hide immense complexity, providing a clean, defined way to interact with systems without needing to be an expert in every single layer.
Okay, so with that really solid understanding of interface, let's put it all together. What exactly is an API, an application programming interface, and why is it such a game changer?
Right. At its core, an API is basically a set of tools and definitions designed for software developers to use, its main purpose,
Hmm.
to provide controlled access to data, and crucially, to offer an abstraction of complex implementations.
Meaning developers don't have to build everything from scratch every time.
Precisely. It means developers don't have to create everything yourself. When an API is well designed, it can make nearly impossible things happen with just a few lines of code. And this isn't just about saving time, though it does that. It's about enabling innovation on a massive scale. Think about it. Smaller teams can now build global services super quickly. It really democratizes technology.
That idea of standing on the shoulders of giants really comes through there. It feels like the whole modern web is built like that.
It absolutely is. APIs fundamentally let developers leverage existing code, existing solutions, avoiding constant reinvention. Take image manipulation, for example. Do you know how to programmatically make a photo black and white? Like dealing with pixel values, color algorithms?
No, definitely not.
Most developers don't, myself included, but with an API, you can often just download an important image package or library.
And suddenly you can do it.
Suddenly you can. You just call a method and bam, the photo's black and white. This whole concept of libraries that package up code to solve common problems so that you don't need to do it yourself,
Huh?
that's the cornerstone of modern software development. It just accelerates everything.
So if I'm hearing you right, while API could technically mean any programming interface,
Mm-hmm.
when people talk about it today, casually, they almost always mean something specific.
You've hit the nail on the head. These days, the term API is almost always used as a way to explain web-based APIs.
Hmm.
It's probably safe to assume that when you hear API in the wild, it's most likely that people are talking about a web-based API.
Okay.
And that distinction, web-based APIs, sets the stage perfectly for our next section. How these remote APIs came to dominate everything, connecting applications across the globe.
We started this conversation talking about a physical remote control for a radio. Great analogy for abstraction, but it also perfectly sets up this idea of a remote API, doesn't it?
It really does. With a physical remote, you press a button, a request gets sent, the actual processing, changing the channel, adjusting volume happens elsewhere.
Right, not in the remote.
Not in the remote, wirelessly, or as the source puts it, kind of colorfully, all a noob in the cloud. This dream of remotely controlling software, accessing data that lives somewhere else, not on your machine, but on a server far away. That was a huge challenge for developers for a long time.
Oh, I bet. Building that from scratch sounds incredibly clunky, like you said. What was it like before a clear standard emerged?
It really was clunky. Developers struggled because, well, there wasn't a standard that everyone loved. There were earlier attempts, like SOP, Simple Object Access Protocol.
Heard of that one, XML-based, right.
Yeah, XML-based, quite rigid, very verbose. It worked, but it was heavy. Then, a new architectural style appeared that was clear and allowed us developers to interact with specific resources over the web. And it quite literally changed everything.
Yeah.
It wasn't just an improvement. It was a genuine revolution in how we built connected software.
And that game changer, of course, was REST.
You got it. REST, or representational state transfer, it just rapidly emerged as the clear winner. Its popularity spread so fast, it became so ubiquitous that it practically became synonymous with API. It's like people say Xerox to mean photocopy, right?
Yeah, even though Xerox is just the brand.
Exactly. That's how pervasive REST became. Now, it's not the end-all, be-all. Things like GraphQL are evolving,
Yeah.
offering different ways to fetch data. But for the vast majority of web APIs you interact with today, you're dealing with a RESTful one.
RESTful. So an API that follows the REST style and constraints.
Right.
Okay, before we dive deeper into what makes an API truly RESTful, it sounds like we need a quick refresher on the web fundamentals REST sits on top of. Like putting on a nice hat, REST needs the head underneath.
Absolutely. A quick whirlwind tour. First, the basic client-server interaction. Your browser, your mobile app, that's the client. It initiates requests to a server, which processes them and sends back responses.
And they talk using.
They talk using HTTP, the Hypertext Transfer Protocol. HTTP is fundamentally a request-response protocol. Send a request, get a response. Simple, but powerful.
And a critical concept for REST is that HTTP is stateless. What does that mean in practice? Why is that so important for APIs?
Stateless means that once that request receives a response, it's all done. The server doesn't remember anything about your previous interaction, every single request from the client.
Has to contain everything needed.
Exactly. It must contain all the information necessary to understand the request. This makes server design much simpler. They don't need to hold on to conversational memories, so to speak. If you need to maintain state, like knowing if a user is logged in, your client, your browser, or app will have to manage that itself and send it up with each new request.
How does it send that state?
Typically using special key value pairs called headers or sometimes tokens. This ensures each request is self-contained and independent.
So when we make these requests, we're not just asking for something, we're telling the server what we want to do with it using different HTTP verbs.
Exactly right. These verbs, or request methods, they clearly state the intention of your request. It's like a universal language for interaction. The most common ones, the ones RESTful APIs really lean on, are GET. This is for reading or retrieving data, just asking for information like viewing a web page or getting a list of products. Shouldn't change anything on the server.
Okay.
POST, used for submitting or creating new data, like filling out a sign-up form or adding a new record via an API.
Right.
PUT or PETCH, these are for updating existing data. PUT usually replaces the whole thing, while PETCH is more for incremental updates, changing just specific fields.
Got it.
And delete, pretty self-explanatory. Used for removing data, deleting a specific item or record, you send a delete request to its unique address.
Makes sense. Beyond the verbs, how does the actual information get passed back and forth? You mentioned headers.
Yeah, there are a few key ways. You've probably seen query string parameters in URLs, the stuff after the question mark. Good for simple bits of info. But headers are really crucial. Key value pairs in both requests and responses. Request headers can say what kind of content you expect back, like application JSON, your preferred language, or they carry authentication info to keep you logged in across stateless requests.
And headers are also key for caching, right? That sounds like a huge performance boost.
Oh, absolutely. Headers like if modified since are fundamental for efficient caching. Your client can ask the server, hey, has this changed since last time I asked?
And if it hasn't?
If it hasn't, the server can just send back a 304 not modified status code. Basically tells the client, use the version you already have, avoids re-downloading the whole thing.
Nice. Saves bandwidth, speeds things up.
Massively reduces network traffic, speeds up perceived load times. It's a really powerful concept for building fast, scalable applications. And speaking of responses, another vital piece of info is the HTTP status code.
Ah, yes, the famous 404 not found. Everyone knows that one.
Exactly. Status codes are vital. They tell you what happened on the server side in a standardized way. 200 OK means success. 201 created means something new was made.
404 means it's not there.
Right. And a 500 server error means something went wrong on the server itself, the one developers hate to see. These codes quickly convey the outcome, making debugging and automated error handling much simpler.
All right, feeling good about those web fundamentals. Now, you mentioned a RESTful constraint scavenger hunt earlier. Are we ready to start ticking off some boxes? What defines a truly RESTful API?
We are. Yeah, to be considered truly RESTful, an API needs to follow several architectural constraints, like design principles. And good news, we've already covered two just by understanding the web. First, the client-server architecture. Your program makes self-contained HTTP requests to a server. Second, statelessness. Remember, the server won't remember anything about the particular client between requests.
So state, like login info, has to be sent each and every request, usually in headers.
Exactly. So boom, you've already got two knocked off our scavenger hunt list.
Fantastic. 2 down. What's next on the list for RESTful qualities?
Next up is the concept of resources. It's a bit abstract, but super important. This is the R in the URL or URI, Uniform Resource Identifier, and it's meant to be broad. We use resource to refer to just about anything that we build or interact with online.
Like what? Give me an example.
Okay, imagine an online bookstore. The books themselves, they're resources. You click a book, you see the author is also a resource. Even collections like all books by this author, or maybe even a group of fans of that author, those are resources too. The key idea is that everything is a resource.
Yeah.
It gives us a consistent way to model things in a RESTful API.
Okay, clients, servers, stateless, everything's a resource. How do we actually do things with these resources? How do we interact beyond just reading?
That brings us right back to CRO, create, read, update, and delete, those fundamental data operations. And RESTful APIs beautifully map these directly onto our standard HTTP verbs. This consistency is key.
So read is?
Read is get T. If you're just getting information to display it, like fetching an author's page or a list of books, your program sends a GET request to that resource's specific URI.
Create?
Create is post. To add a new author or a new book, you'd post data to, say, an author's or book's endpoint. Clearly signals you want to create a new resource in that collection.
Update?
Update is usually put T or patch VH. Patch is often preferred for partial updates, just changing an author's bio maybe. Put T implies replacing the entire author record.
And delete?
Delete is delete. Simple. To remove an author or book, send a delete request to that specific resource's URI.
That is really elegant. Using standard web verbs for common data actions makes the API feel predictable, intuitive. Easier to learn, I imagine.
It truly does. This adherence to existing web standards, not inventing something new, is what made REST so powerful and consistent. It just made sense, driving its massive adoption.
This has been great for the foundations, but what if we actually wanted to see a RESTful API in action? Play around with one. I hear there are some cool public ones.
Oh, definitely. And they're surprisingly accessible. A really excellent example is Spotify's RESTful API. They offer an interactive developer console right in your web browser.
Oh, nice.
Yeah, it's super user-friendly for experimenting. You can explore all sorts of fascinating data, find a song's danceability, its beats per minute, even analyze its structure like verses and choruses. Developers build amazing things with this. Music festival apps, suggesting bands based on your listening, tools for DJs. Lots of possibilities.
So what does the data look like when you get it back from Spotify? Is it just raw text?
Typically, API responses are in JSON JavaScript object notation. Think of it like a lightweight, human-readable way to structure data using key-value pairs, like an address book, basically. Makes it super easy for different systems to understand each other. And for big data sets, responses are often paginated. You get results in chunks, like page 1, page 2, so you don't get overwhelmed.
Sensible. And you mentioned authentication before. OAuth tokens. Need to be careful with those.
Absolutely. Vital point. When you work with APIs, especially ones needing login, you'll use oath tokens. They're like temporary, secure digital passes. Instead of giving an app your main password.
You give it a token with limited permissions.
Exactly. It proves who you are and grants specific limited permissions for a set time. If a token gets compromised, your main account is still safe, so you must keep them private. In demos, you might see one briefly, but never ever expose them in real application code that users can see.
Okay, clear warning. Can you walk us through a conceptual demo, like searching for an artist on Spotify's console?
Sure. Imagine you're in their developer console. You log in, it gives you an oath token automatically. Then you find the search for item endpoint. Type in Beyoncé.
Okay.
You click Try It. Instantly, the API sends back a JSON object. It'll have a list of artists matching Beyoncé, including details like her massive follower count, genres. And what's really cool is, in that response, you'll get her unique artist ID.
Ah, so you can use that ID for other things.
Exactly. You take that ID, go to the artist's endpoint, and ask for all of the artist's albums using that ID. The API responds with another JSON list, all her albums, even URLs for the album art. Shows how resources are interconnected.
That sounds incredibly powerful for building music apps. And you mentioned speed earlier. Does caching play a big role there? How fast those results come back?
It absolutely does.
Oh,
That
God.
speed is a prime example of cacheability in practice, a core REST principle. Beyoncé's info, her album list, that stuff doesn't change every second, right?
Right.
So Spotify's API likely uses a layered system of caching heavily. Frequently requested data isn't fetched from the main database every single time. It's stored temporarily, maybe on a server-side cache, a proxy server closer to you, even your browser's cache. As the API user, you don't necessarily care how it's cached, just that the data is available and fast when you hit that URL. It's crucial for the efficiency and scalability of huge services like Spotify.
Okay, Spotify is great for getting data. But what about doing something more tangible? Like actually sending a text message. Can APIs simplify something like that?
Oh, absolutely. And Twilio's API is a fantastic example of that power through abstraction. Twilio makes sending text, making calls, even building interactive voice menus incredibly simple. It abstracts away all the messy details, different cell carriers and standards and phone numbers all over the world. As a developer, you don't need to know any of that.
You just tell Twilio, send this message to this number.
Exactly.
Yeah.
And it just works. This kind of abstraction lets small startups offer features that used to need massive telecom infrastructure. It's really empowering.
So how would someone get started with Twilio to actually send a text?
You can usually sign up for a free Twilio trial account. There might be limits like only sending to phone numbers you've verified first, but it's perfect for hands-on learning. Once you're in and have a Twilio number, you'd look at their API documentation. It's generally excellent. You'd find the message resource section, specifically how to create a message. They usually provide code examples in lots of languages, including how to do it directly using a command line tool called curl.
Ah, curl. Heard that name.
Right.
How does that fit in? Especially if you're just, poking around an API.
Curl is an open source tool, and it's genuinely awesome for poking around at APIs right from your computer's terminal or command line. Think of it as a Swiss Army knife for making raw HTTP requests.
How do you use it?
Basic usage is simple. Curl, followed by the URL you want to hit. If you need to send data or use spaces, you put things in quotes. It's fundamental for developers to quickly test if an API endpoint is reachable, make direct calls, or see the raw response for debugging.
Any quick test you can do.
Yeah, a fun one is curl.icanhasdadjoke.com. Just gives you a random dad joke back. Simple way to see if curl's working.
Ah, love it. So could I use curl to do that Spotify Beyonce album search from my own machine?
You absolutely could. You'd construct a curl command. You would need the specific Spotify API URL for albums, Beyonce's ID, and crucially, the right authentication headers with your OAuth token.
Yeah.
You'd get the raw JSON response spat out right there in your terminal.
Raw JSON. Sounds like it could be hard to read.
It can be, especially for complex responses. That's where you might pipe the output into another command line tool called JQ. JQ takes that raw JSON and makes it very nice and pretty, colorized and formatted, even filterable, right in the terminal. Curl also handles stuff like URL encoding automatically. If your search has spaces, curl turns them into plus signs in the URL, which you might forget if you were building it manually.
Okay, so curl for Spotify. What about sending a Twilio text with curl? How would that look down in the weeds?
For Twilio, you'd make a PUIST request to their message resource endpoint. You'd include parameters using flags like SNID or data URL encode. So from your Twilio number, body your message, API test, to your verified phone number. And critically, you'd pass your private account SID and auth token for authentication. Curl has an IU flag for basic auth, which is common.
And if it works?
If it works, you'd get a 201 created status back in the terminal, and like magic, boom, you got it on your actual phone.
Cool.
Then you could use a GET request with curl to the same message URL to retrieve a message log, seeing the status of the message you just sent. But while curl is powerful for testing, it can get clumsy or challenging for more complex requests with lots of parameters. Syntax can be tricky, especially across different operating systems.
Right. So curl's great for quick pokes, but maybe not for managing lots of API calls or really long, complex commands day to day. Are there more user-friendly visual tools?
Definitely. And that's exactly where visual API clients like RESTfox or Postman come into play. They're designed precisely to make managing and making API calls much easier, especially with those long commands or when you need to handle credentials securely. RESTfox, for example, lets you organize your API calls into folders, like a Twilio folder. Keeps everything neat and easy to find again.
And how would those tools handle our examples, like sending a Twilio message? Make it more intuitive.
Yeah, in RESTfox, you'd create a new request, maybe call it send message. You'd select post from a dropdown. Then you'd have clear input fields for the URL and for the body parameters. From body to, you could even add a media URL field if you wanted to send a picture.
No wrestling with command line flags?
Exactly, just fill in the boxes. Then you could make another request, incoming message log, set it as DT, and maybe add a query parameter to your Twilio number to filter. Click send, and you see the nice formatted JSON response showing messages you received.
What about those sensitive credentials, the auth tokens, account SIDs? You stressed keeping them private. How do visual clients help, especially if you want to share requests with a teammate?
This is where they really shine for security and collaboration. Tools like RESTfox let you store sensitive info like your account SID and auth token as environment variables. So you don't hard code them directly into the request itself. Instead, your request might reference a variable, like Twilio counts it.
So the request itself doesn't contain the secret.
Correct. It's way more secure. And it makes your collection of requests shareable. You can share the collection file, your teammate sets up their own environment variables with their credentials, and the requests just work for them. No secrets exposed.
And Postman. That one comes up a lot in industry.
Postman is a really powerful enterprise-ready tool. Loads of features. Big thing is shareable collections. Many companies actually publish official Postman collections for their APIs, making it super easy to get started. One really cool thing Postman does is code generation. If an API doesn't have a helper library for, say, Python, you can build the request visually in Postman. Then click a button, and it generates the Python code, or curl, Node.js, Java, to make that exact request.
Wow, that sounds incredibly handy.
It's really handy, especially when you're trying to integrate an API quickly and don't want to sift through tons of documentation just to figure out the basic request structure.
So these visual tools make sending requests easier. Can they also help demonstrate concepts like client-side caching visually?
Yes, beautifully. You can make a GCO request in Postman or RESTFox for, say, an image URL from an API. Look at the response headers, you'll see a last modified date.
Okay.
Now, make the exact same request again, but this time you add a request header. If modified since with that date you just got. If the image hasn't changed on the server since that date, the server response will be different. You get a 304 not modified status code back, and crucially, the response body size will be tiny, maybe 0 bytes back.
Ah, because it didn't send the image data again.
Exactly. It visibly shows caching in action. Your client avoided re-downloading something it already had. Powerful illustration of efficiency.
That's super clear. Now, you mentioned earlier that some companies provide helper libraries or SDKs. How do those fit in? What more do they abstract away?
Right. Helper libraries or SDKs, software development kits, they take abstraction to the next level. They let developers interact with an API using their native language, Node.js, Python, Java, Ruby, whatever they're comfortable with. This means you often don't even have to think about constructing the underlying HTTP request like we did with curl or visually in RESTFox. You don't have to parse the raw JSON responses yourself. The library handles all that.
So it feels more like just writing regular code in that language.
Exactly. It makes it feel like you're actually working with these objects directly in your programming language, not just sending messages over the internet.
Can you give an example? Like, how would that Twilio text message look using their Node.js helper library?
Sure. Instead of that long curl command with the data Erlang code and authentication flags, in Node.js with the Twilio library, it might look as clean as this. Client.messages.create from your Twilio number, body, hello from deep dive to recipient number.
Wow, that's much shorter and clearer.
Right. It feels very similar to writing any other JavaScript code because the library abstracts away all the HTTP API things. It handles forming the request, setting the POST verb, adding authentication, sending it, and parsing the response for you.
What about timing? APIs aren't instant. How do libraries handle waiting for the response without freezing the whole application?
Great question. That gets into asynchronous programming, which is absolutely crucial. When your code calls an external API, it can't just stop and wait, or the user interface would freeze. Modern languages use concepts like promises or async await in JavaScript, or then catch blocks. This lets your app send the request, then go do other things, and only come back to handle the API response when it actually arrives. It keeps everything running smoothly.
And helper libraries manage this async stuff for you.
They do, very elegantly. They provide functions that return promises or support async await, hiding the underlying complexity of managing those network calls without blocking.
Do helper libraries also make error handling better, more specific?
Definitely. Instead of just getting back a generic HTTP 401 unauthorized error, which could mean a few things, a good helper library might give you a specific error code directly from the API provider. Like Twilio might return error code 2003 if your auth token is wrong, or 21201 for an invalid phone number format. These specific codes are much easier to diagnose and handle programmatically in your application logic.
That sounds super useful for automation, too.
Hugely useful. Helper libraries are great for automation-based tasks or batch scripting. Imagine you want to delete all the messages in your Twilio account. You could use the library to first list all messages, client.messages.list, then loop through the list and call message.remove on each one. The library takes the raw JSON data from the API and inflates it into proper objects in your programming language, making it feel like you're actually working with these objects, not just raw data strings.
This all ties back really nicely to one of our RESTful constraints, doesn't it? The idea of uniform design.
It does perfectly. Helper libraries work so well because the underlying REST API usually provides enough information in the response, like URIs for specific resources, e.g. the URI for a specific message you want to delete. This makes it clear how we could modify and delete the resource.
That's the resource manipulation through representations part.
Exactly. And the consistent, uniform use of the HTTP verbs get, post, delete for CRUD ensures that whether you use curl, a visual client, or a helper library in Python or JavaScript, the API behaves predictably. It feels natural and consistent for the developer, no matter the tool.
Okay, so we've really explored APIs, seen the tools. Now let's talk about taking this and building something real, something visual and interactive. Let's dive into building a web application using Vue.js. What is Vue.js and why pick it?
Right. Vue.js is a very popular JavaScript framework for building applications and websites. Its main goal is to help you make your websites and apps faster and more dynamic. It gives you that snappy, interactive feel users expect.
What makes it popular?
It's known for being lightweight, pretty easy to get started with. Even adding it into existing projects isn't too hard. And it provides useful tools out of the box, along with a set of standards for code organization, which helps keep projects manageable. It uses something called a virtual DOM internally for efficiency, but honestly, that's an optimization detail, not important for understanding this course. The key is it makes building interactive UIs easier.
Can you walk us through some basic Vue concepts? How do you even get a Vue app started?
You usually start with a simple HTML file. You can include Vue using a CDN link, just a script tag. Then in your own JavaScript, you use vue.createApp to create your Vue application instance, and you mount it to a specific HTML element on your page, maybe a div with an ID.
And anything inside that div can now be controlled by Vue.
Exactly. That element becomes the root of your Vue application. Now you can make things inside it dynamic and interactive.
Like making parts of the page appear or disappear.
Yeah.
Or handling clicks.
Yep, that's where views, directives, and events come in. For showing hiding things conditionally, you use directives like vif or vshow. Really handy for showing a loading spinner or toggling a menu. Makes the UI respond to data changes. For user interactions, you use vion, or its shorthand, @epi. You can listen for standard browser events, like at click on a button, or even at keyup.enter on an input field.
And what happens when those events fire?
You define methods, basically. JavaScript functions within your Vue instance. When the event happens, the corresponding method gets called. You can even pass data from your HTML template directly into those methods as arguments.
Now, for bigger apps, you wouldn't put everything in one file. How does Vue handle reusable UI pieces?
That's where components are essential. Think of components as custom, reusable building blocks for your UI, like creating your own HTML tags.
How do they talk to each other, like pass data around?
Good question. Data typically flows down from a parent component to a child component via props. So a parent list might pass a photo prop down to a child image card component. If the child needs to send information up, maybe tell the parent it was clicked, it doesn't change the prop directly.
Yeah.
That's bad practice, mutating props. Instead, it emits an event. The parent listens for that specific event and can then update its own data or take action. Keeps data flow predictable.
Gotcha. Props down, events up. What about displaying lists of things, like a photo gallery from an API?
For that, Vue has the v-for directive. It lets you loop over an array, maybe an array of image objects fetched from your API, and render an HTML element, like your image card component, for each item in the array.
Okay.
Super important when using v-for. You must include a key prop on the element being looped. This key needs to be unique for each item, like an ID. It helps Vue efficiently update the list when data changes, performance, and avoiding bugs. Your developer tools will even yell at you if you forget it.
Good to know. Okay, solid foundation. Let's make it concrete. Let's talk through building that Pickle photo sharing app conceptually. Users text photos, they show up on a web page, connects APIs to the front end.
Right. For Pickle, you'd start maybe with a basic HTML template, index.html, maybe with some nice styling already done. You integrate Vue.js into it. Initially, just to get the layout right, you might use dummy image URLs from PlaceKitten or PlaceBear as placeholder data in your Vue app.
And you can just open that HTML file in your browser locally to see it.
Yep, just open index.html locally. You'll see the static page. The app itself uses Vue as a front-end framework to manage the UI, and maybe another library like Silentbox for those nice image pop-ups when you click a photo. Both Vue and Silentbox provide their own internal APIs for interaction within the browser.
Okay, local web page works. How do we get it online? And crucially, how do we handle those incoming text messages that are supposed to power the gallery?
This is where hosting has changed so much. We've gone from managing physical servers to the cloud, and now increasingly serverless setups. Twilio Functions is a great example of serverless. It lets you run back-end logic, small bits of code on demand, without managing any servers yourself.
So you can just upload your index.html file.
Pretty much. You upload your index.html to Twilio Functions, maybe mark it as public, deploy it, and boom, you instantly get a live URL on the internet.
Okay, web page is live. What about the texts? How do they trigger something in our backend without us constantly checking?
That's the magic of webhooks. A webhook is basically an automated notification. When a message arrives at your Twilio phone number, Twilio automatically sends an HTTP POST request to a specific URL you configure, in this case, the URL of another Twilio function.
So it triggers your code automatically when a message comes in?
Exactly. You set up your Twilio number to point incoming messages to, say, an incoming message Twilio function. So you text a photo, maybe that beautiful burrito, to your number. Twilio calls your function. Your function's logs would show the message details, the image URL. And the function could then process it, maybe send back a "thanks for your submission" reply using TWML,
TWML.
Twilio markup language. It looks a lot like HTML, but it's specifically for telling Twilio how to respond via voice or SMS.
Okay, so we have the front-end web page live and a back-end function triggered by incoming texts. But how does the front end get the photos to display? The back end needs to serve them up somehow.
Precisely. We need to bridge that gap. That's why we design a custom API within Twilio Functions. A new function, let's call it the Pix API. Its only job is to be the back-end data source for our Vue.js front end.
So the front end will call this Pix API.
Right. Initially, maybe this Pix API just returns hard-coded image data just to get the front end connected. But then you'd update it. It would use the Twilio helper library, like we discussed, to dynamically list all messages sent to your Twilio number. For each message, it would then access the associated media images via sub-resources, like message.media, to find the URLs of the actual submitted photos.
And the crucial part here is making sure the data comes back in the format the front end needs. That data shaping step sounds important.
Oh, absolutely critical. Data shaping or transformation. The raw data from Twilio's message objects might not be exactly what your Vue front end wants for its gallery. So your custom Pix API function would shape that raw data into a specific JSON format, maybe an array of objects where each object has src, description, and alt properties exactly what your Vue component expects. You might even need to clean up the URLs, like remove JSON extensions from media URIs. Twilio sometimes adds to get the direct image file link. This shaping ensures the backend serves data the way the client needs it.
So if you visited the Pix API URL in your browser,
you'd see that perfectly structured JSON array of submitted photos, including the burrito, ready for the Vue app to fetch and display.
This really sounds like it aligns with the uniform interface REST constraint again.
It does in many ways.
Yeah.
The Pix API response includes clear URIs for resources, the image URLs. There's resource manipulation through representations because the front end gets the info it needs to display the image. And self-descriptive messages because the response includes headers like content type application JSON telling the client how to parse it. However, it's worth noting, as a little foreshadowing. While functional, this simple app probably doesn't fully satisfy one key, often overlooked, REST constraint. Hideo asks hypermedia as the engine of application state. We'll circle back to that very important point at the end.
Okay, teaser noted. So backend API is serving Pix in the right format. How does our Vue.js front end actually consume this API and display the photos, bringing Pickle fully to life?
Right, the final connection. The Vue.js app uses the browser's built-in Fetch API. It's a modern way to make network requests from JavaScript. We make an async request to our custom Apex URL. Using async and await ensures the browser doesn't freeze while waiting for the network response.
It waits for the JSON data.
Exactly. It awaits the response, then parses the JSON content using response.json. Once that array of image data is ready, it's used to update the Vue application's gallery data property.
And because Vue is reactive.
Because Vue is reactive, as soon as that gallery data changes, the UI automatically updates. The submitted photos, including our burrito, just appear on the web page. No manual DOM manipulation needed. That completes the whole end-to-end flow.
That's a fantastic walkthrough. Really connects the dots. But for bigger, more complex projects, I imagine developers need more structure, more advanced tools than just a single HTML file and a CDN link. Where do they go next?
You're absolutely right. For larger apps, managing lots of components in separate files, handling build processes, optimization, it gets messy fast if you're doing it manually. That's where the Vue CLI command line interface is invaluable. It's a tool that simplifies project setup massively. You run one command, Vue create, and it generates a whole structured project for you.
What does that generated project look like?
It gives you a standard best practice layout, an src folder for your source code components, views, JavaScript logic, a public folder for static assets like the main index.html file or favicons. It also sets up sophisticated build tools like Webpack behind the scenes to handle bundling, code splitting, optimization, all that complex stuff.
And it helps with navigation within the app too, like different pages.
Yes, Vue CLI projects often integrate Vue Router right from the start. This lets you build single-page applications, or SPAs.
In an SBA, navigating between pages doesn't require a full browser refresh. It just swaps out components, making the experience much smoother and faster. ViewRouter uses tags like router_view to display the component for the current URL and router_link for navigation links. Within this structure, you often talk about views, the main components mapped to routes, and smaller reusable components that make up those views.
How does styling work in these more structured Vue projects? Is it just one giant CSS file?
You have options, which is nice. You can have global styles, maybe for branding, fonts, basic layout, imported into your main JavaScript file, main.js, from CSS or Sass files. These apply everywhere. But Vue also has a fantastic feature for component-specific styles. You can add a scoped attribute to the style tag right inside your .vue component file.
Scoped, meaning
Meaning those CSS rules will only apply to the elements within that specific component. It prevents styles from accidentally leaking out and affecting other parts of your application, which is a huge help in preventing CSS conflicts in large projects. The build tools also handle assets like images referenced within your component seamlessly.
what about managing the actual data in these bigger apps, like a full shopping cart, adding, removing items, calculating totals?
Yeah, front-end data management gets more involved. You'll quickly move beyond hard-coded data. You'll fetch dynamic content using Vue's mounted lifecycle hook, code that runs when a component is added to the page, and the Fetch API, pulling data from your backend API. For something like a shopping cart, you'd implement the CRU operations, add, update, delete by having methods in your component that modify its data properties, like an array of cart items. Vue's reactivity takes care of updating the display.
And calculating things like the total price.
That's a perfect use case for computed properties. A computed property is like a derived value. You define a function, say cart total, that calculates the total price based on the items currently in the cart data. The magic is Vue automatically tracks the dependencies. Whenever the items in the cart change, the cart total computed property automatically recalculates itself. You don't have to manually trigger updates. Super clean and efficient. And for really large applications where many different components might need access to the same data, like user login status or the cart itself, you might reach for a dedicated state management library like Vuex to centralize that shared state. But that's definitely getting into more advanced territory.
I've also heard about something called the composition API in Vue. It sounds like a different way to write components.
It is, yeah. It's an alternative to the traditional options API we've mostly discussed, with data, methods, computed sections. The problem with the options API in very large components is that logic related to a single feature can get scattered across those different sections, making it hard to follow.
So the composition API tries to fix that.
Exactly. The composition API, usually used with a setup attribute on the script tag, offers a more functional approach. It lets developers organize our code logically by feature rather than by option type.
How does that work in practice?
Instead of a data section, you declare reactive variables directly within your setup function, using ref for simple values like numbers or strings, or reactive for objects. Vue tracks these for updates, and instead of separate methods or computed sections, you define functions directly. You use helper functions like computed to create derived reactive values, and watch to explicitly react to changes in specific data. The big benefit: you can group all the reactive variables, computed properties, and methods related to a single piece of functionality together in one place. Makes the code much more concise, readable, and maintainable, especially as components grow complex. It was a really positive evolution for Vue developers.
Okay, switching gears a bit. Building complex apps is one thing, but making them perform well under load is another huge challenge. How do developers think about performance and scaling?
It's crucial. We talk about speed, which is really about the single user experience. How fast does it feel? Factors there are network latency, number and size of requests, HTTP versions, compression. Then there's scaling, which is about multi-user performance. How well does the app handle lots of users at once or sudden traffic spikes? Think students checking exam results all at the same time.
How do you even measure performance? It seems subjective.
There are objective tools. Lighthouse, built into Cron's developer tools, is a standard one. It loads your page and measures key metrics, giving you scores and diagnostics. It looks at things like first contentful paint when something first appears, speed index, how quickly stuff fills in, largest contentful paint when the main content is visible, time to interactive when the user can actually use the page, total blocking time, how long the page is frozen, and cumulative layout shift, how much things jump around unexpectedly. Gives you a concrete dashboard.
And architecturally, what components affect scaling?
You've got your servers. Front-end servers sending the HTML, JS, CSS, data servers holding the data. You'll often have load balancers distributing requests across multiple servers so no single one gets overloaded. Proxies can act as intermediaries, often used for caching. The network itself matters mobile versus broadband. And the application logic itself is heavy on data processing or mostly serving static images and scripts. Developers have control over resource structure, how many API calls are made, data sizes, and, critically again, cacheability.
Caching, it just keeps coming back. It sounds fundamental for both speed and scaling.
It is absolutely fundamental. Caching is storing responses so they can be reused for future requests, improves speed, drastically reduces server load.
Where does caching happen?
Multiple places. Server-side caching, proxy caches, like CDNs, network router caches, and very commonly client-side caching right in the user's browser. And crucially, it's largely developer-controlled using those HTTP headers we talked about. Cache control, max age, how long to cache in seconds, expires, a specific expiry date. Setting these correctly is vital. Caching is a core part of the REST architecture and very important for scalability. It saves immense computation globally.
Okay, apps built, performance-tuned. Now, the really critical, sometimes thorny topic, security and privacy. What's the key difference and why does it matter so much?
Super important to differentiate. Privacy is mainly about personally identifiable information, PII, data that can identify someone. It involves regulations like GDPR or HIPAA, user rights, what data you collect, why, and who you share it with. It's about ethics and compliance. Security is the how. It's about safeguarding that data through technical measures, good coding practices, monitoring against attacks, preventing breaches.
You have one without the other.
You can, and it's bad either way. Privacy without security. Maybe you have good policies, but your data leaks, like Cambridge Analytica. Security without privacy. Maybe your data is locked down tight, but the company collects way too much and sells it without clear consent. You need both.
What kind of sensitive info should developers be thinking about?
Both direct stuff, passwords, bank details, health info, address, and indirect stuff that can be inferred, like location patterns, purchase history, social connections. Even metadata can be sensitive. Developers must be aware of relevant regulations and handle data responsibly. Ignorance isn't an excuse.
What are some practical security measures on the front end where users interact?
Okay, front end. Cookies are common. First-party cookies are often needed for login sessions, but third-party cookies, used for cross-site tracking, are now widely blocked by most major browsers due to privacy concerns. Huge shift there. Then there's cross-site scripting, XSS. Malicious scripts injected via user input, maybe in a comment form, need strong server-side validation and careful client-side handling, like escaping output. Cross-site request forgery, CSRF, is trickier. An attacker tricks a logged-in user into performing actions on another site unknowingly. CSRF tokens, unique short-lived tokens embedded in forms, help prevent this. And cross-origin resource sharing, CRS, uses HTTP headers like access control, allow origin to tell the browser which other websites are allowed to make requests to your API or resources, restricts malicious scripts on other domains.
And on the back end and during deployment, that sounds even more complex.
It's a huge area. Supply chain attacks are a big worry. Vulnerabilities in the third-party libraries everyone uses, like the Log4j incident. Makes version pinning, locking down exact library versions, critical. Endpoint security, using TLS HTTPS for all server-to-server communication is essential. Encrypt everything in transit. Systems need proper authorization. Only talk to known, trusted clients. Denial of service, DOSI, attacks. Try to flood servers with requests. Needs network-level protection. Rate limiting. DevOps practices like CI/CD pipelines help automate security checks during development and deployment. For passwords, NIST guidelines now emphasize length and checking against known breaches over forced complexity, because users just make predictable patterns. Servers must store only encrypted passwords with strong salts. Secret management is vital. Keep API keys, database passwords out of your code repository like Git. Use environment variables or dedicated secret vaults. And logging, essential for debugging and spotting attacks, but needs balance to avoid performance hits or logging too much sensitive data.
Wow. It's not just one thing, is it? It's a whole mindset, a continuous process across the entire development lifecycle.
Exactly. Application security is a vast topic. It requires breadth of knowledge from app developers. They are ultimately responsible for the privacy implications and security implementations. Collect only what you need, protect it rigorously. The golden rules. Validate input, encrypt output, never hard-code secrets.
What an incredible journey today. We really have covered a lot of ground, haven't we?
I really have.
From breaking down interface and abstraction, through the rise of APIs and REST, getting hands-on with tools like curl and Postman and helper libraries, then conceptually building and deploying a Vue.js app, seeing components and reactivity in action. And finally, tackling the huge topics of performance, scaling, security, and privacy. Whew.
It really highlights that core theme of abstraction, doesn't it? APIs, helper libraries, frameworks like Vue. They all provide these powerful layers. Just like you use a radio without knowing electronics, developers use these tools to build incredibly complex systems without needing to understand every single bit underneath. That's the real power of modern development.
It truly is. And as we hinted earlier, our simple pickle app, while it worked, didn't fully embrace that one advanced REST constraint, Hadio-ass hypermedia, as the engine of application state.
Right. The idea that a truly RESTful API doesn't just send data back, it also includes links within the response that guide the client, telling it what actions are possible next, what related resources exist, makes the API much more self-descriptive and discoverable.
So, for your provocative thought today, consider this. If the applications you build or the APIs you use don't fully embrace this self-descriptive, hypermedia-driven nature, how might that limit their long-term flexibility, their ability to evolve easily? And maybe more personally, in this constantly changing tech landscape, how can you ensure your own knowledge stays as fresh and relevant as cacheable, maybe as a well-designed API response?
Something to definitely mull over as you continue your own deep dives into this fascinating, always evolving, interconnected world.